Now it's more about another interesting topic about, let's say, gas diffusion for reduction of CO2. We have Guoliang Chen. I'm sorry if I didn't pronounce that in a correct way.
Yes, it's correct.
Guoliang Chen is a final year PhD student supervised by Professor Hao Wang and Associate Professor Li Ji. His research interests are in applying advanced gas diffusion electrodes for electrochemical reduction of CO2. Floor is yours, Guoliang, to share your research.
Okay.
Thanks. Yep, we can see your screen. Oh, you unshare it. Yep, all good with that.
Okay.
Thanks.
So it's the full screen or just a small window?
No, it's perfect. Yep.
Oh, it's okay. So I will start. So hello everyone, I'm Guoliang Chen. So I'm in my final year PhD project. So my supervisors are Professor Hao Wang and Associate Professor Li Ge. So today my research topic is mainly about my PhD project. It's about advanced gas diffusion electrodes for electrochemical conversion of CO2. So first of all, I'd like to give you guys a little bit background about this. So as we know, all the research hotspots is like energy conservation, CO2 capture, decarbonization. So the energy is like the power usually covers like from two renewable energy and conventional energy like natural gas and coal. So the conversation process and infrastructures like we can use like renewable energy to provide electricity for electrolysis, convert CO2 to fuels and other value-added chemicals. Also like methanation, conventional part like we can dry reforming CO2 and water become methane and hydrogen and the syngas. Also syngas CO and hydrogen mixture. So all these processes like to capture CO2 and regenerate powers. So what's the difference? What's the like improvement for the catalyst part? For the conventional conventional part, which will always require like high energy input, which requires like high pressure and high temperature. We need a lot of energy input to like to burn traditional fossil fuels to provide energy to transform the chemicals to very useful chemicals. But for electro process, we can use a very compact and small electro cell to convert the CO2 by use renewable energy provide electricity to useful chemicals. So we can also operate at ambient pressure and temperatures. So here I'll give you guys an example about we capture CO2 from the flue gas. We use some we can use some adsorbers to absorb CO2 and separate CO2 and use CO2 as a gas as a feed to electro cell. Here I have to say in electro cell is mainly includes two parts like cathode part and anode part. For cathode part is about CO2 electrochemical reduction, but for anode part is oxygen evolution. So we mainly focus on the cathode part. So CO2 can be converted to different chemicals, mainly about the liquid products and the gas products. For this liquid products, it's mixed with electrolytes. We need to like purify it from the electrolytes. Also for the gas products, it's mixed because CO2 is not 100% to convert to other products. It's most of CO2 released, most CO2 contains in the gas emissions. We also need to separate the CO2 with other useful gas products like CO and methane or ethylene. So my research, as I said, I focus on the cathode part, the electrochemical reduction of CO2. So in the early stage of the research for this kind of research, people use H-cell. H-cell is like people directly put CO2 in the electrolytes, and they use electrode like some planar electrode, as like mantle foil, mantle foam. So the CO2 gas will first dissolve in the electrolytes, but gas dissolved in liquids has very low solubility. Here the CO2 gas is like 33 millimole, very low solubility. And the dissolved CO2 need after a very long diffusion path to the active size. It's like 50 micrometer. So it's a long way. So, but if we use gas diffusion electrode, it's like we push the gas through a gas diffusion layer and directly let the CO2 gas arrive at active catalyst size. So the gas only transport from the gas phase. It's very fast. So the distance will be significantly shortened to 15 nanometers. It's like from micrometer to nanometer. So here for our research, as we say, for our research, as we see this GDE, the conventional planar GDE, includes a lot of pieces to assemble it to. But for our research, we use a tubular hollow fiber gas diffusion electrode. Here we can see we only need to seal the inner part of hollow fiber. We can take the inner side, the lumen side of hollow fiber as a gas chamber. We directly push as a video. I can show you guys a video here. So the gas from the inner part and penetrated through the walls of hollow fiber and reach to the catalyst site. So also same as the planar GDE, the diffusion path is then shortened like 50 nanometer. Here also this special designed shape, and it got a very high surface to volume ratio, and also this is like kind of self-support 3D structure. So from the bottom right picture here, I can show you guys like the gas penetrated through the inner side of the hollow fiber, and the reaction happened at the surface of the hollow fiber GDE. So due to the configuration of the hollow fiber, the CO2 gas quickly diffused to the active size. So it will like create a lot of triple phase boundaries, which the reaction happens very fast. So the CO2 gas with different electron and protons will convert to different products. Here I list several like CO, formic acid, and ethylene and alcohol. So how does this hollow fiber fabricated? So it's like we need some metal source here. Like here I examine is copper powder. We also can use like silver, titanium, nickel powder. Also they are related oxide, metal oxide like copper oxide. So also we need a polymer binder. Here I use PEI, so you can use PEI. And also organic solvent. AMP here is fine, and also TMF is also fine. So we put all these things together into a ball mill jar, and we ball mill it like in a low speed, 300 RPM for 24 hours. We can get a very homogeneous polymeric dope. So once this dope is ready, we put it in a extruder. So the AMP is very unique when it reach contact with liquid. It will spontaneous solidification. Not only the outside the AMP, when this dope contact with water, also the inner side. So I show you guys a video here. So we can see the liquid polymer dope, when it contacts with water, it will solidify with this kind of tubular shape of this hollow fiber. So once this tubular shape hollow fiber, green fibers made, we dry it and calcine it in a tube furnace. First, we use air to remove the polymer binder, and these metal powders will become their related metal oxide. They are highly non-conductive, so we also need to reduce it. We can use a chemical reduction combined with thermal reduction to make it to remake it like this shining color of metal. So here I want to talk about our recent studies. I will mainly focus on this catalyst nano engineering, the catalyst engineering, the electrolyte interface, also the CO2 distribution and the triple film, the build of creation of triple phase boundary here. So in the first case of this first case study here, I want to talk about these studies we designed a zinc catalyst with tailored phase for syngas production. This work is based on our previous work, because our previous work is focused on the liquid products. We use electrodeposition technique, deposit tin and bismuth catalyst for formic acid. For this work, we focus on the gas product like CO. We go to metal catalysts. Here is silver and zinc. Zinc is very unique and is non-toxic and is very abundant in Earth. So, and zinc got two main crystal phases and has different reaction selectivity. So if the zinc 101 crystal phase is highly favorable for CO2 to CO production, and zinc 002 is preferred to produce hydrogen. And the mixture of CO and hydrogen is syngas. Syngas kind of different ratio of CO and hydrogen. So how can we regulate the ratio? So we done a lot of research. We found that the cationic surfactant CTAB. So CTAB, when we introduce CTAB in the deposition process, the CTAB will regulate the nucleation and the crystal growth of zinc, and also lower the surface free energy of zinc different crystal. Here it will lower the surface free energy of zinc 101, favorable the growth of zinc 101. Here we can see we got, if we add CTAB, we can get a small morphology of the zinc nanosheets. Here we also investigate, we add in different concentration of CTAB, so how it regulated the morphology of zinc nanosheet. We can see from 0 to 1 millimole CTAB, the nanosheets morphology become much smaller. And also we also regulate the crystal phase ratio of zinc 101 and zinc 002. So we can here with 1 millimole additional CTAB, the zinc got a very high ratio of zinc 101 to zinc 002 to 9.58. Also, when it reflects on the selectivity of the CO2 products. We found that this zinc catalyst shows the best performance with a high ratio of CO2 hydrogen ratio, and the best selectivity of CO around 70%, and the high production rate of syngas. So here I list a short conclusion here is we use pulse electrodeposition technique to control the morphology of sheet structure, and also we add CTAB to affect the nucleation and the crystal growth of zinc. We also the CTAB can also regulate the surface free energy of zinc 101, zinc 102. And also this hollow fiber configuration can provide sufficient CO2 to active size. So based on the previous study, I found actually due to the zinc catalyst, because it has zinc 002 and zinc 101, so it's hardly to improve its selectivity for CO to more than 80%. So I found if we can introduce another metal in this catalyst, maybe we can improve the selectivity of CO product. So I tried different metals, but here I found I use a very facile and convenient method, just immerse this zinc nanosheet-based hollow fiber into silver ions, but the silver ion definitely need to have the surface inorganic ions, because the galvanic replacement will spontaneous happens when these two together, the silver ions will be reduced to silver. So the first stage of nucleation, the silver atoms will aggregation together. But if you don't have the sulfate ions here, it will grow into nanoparticles. But if you got the sulfate ions, it will regulate the growth of the directions and prevent aggregation of silver nanoparticles. It will help to form the sheet structure, nanosheet structure. Here the SEM can show in different stages. In the first stage is the zinc. In the first stage is silver nanoparticles. Two stages silver nanoparticle with nanosheets, and the third stage is the final stage. The nanoparticles are disappeared with the nanosheet structure. Dense and abundant nanosheet structure with zinc nanosheet structure together. Also, the zinc we can confirm with the XRD result and the TEM result. The XRD result of this shows the zinc 111 crystal phase confirmed by HRTM result with this 0.236 latitude. Also, with the introduction of silver into zinc, it will adjust the electronic state of zinc. We saw from the SPS spectrum the metallic zinc shift towards a very high binding energy, and the metallic silver towards to negative binding energy. It means it because of the high withdrawing ability from the zinc. So this kind of combination of synergic effect between zinc and silver could help facilitate the adsorption of intermediates and promote the selectivity of CO. So here we got some very good results. Here from the figure B, the double capacity layer, which can estimate the electro surface area. So we found this candle with the addition of silver actually can increase the ECSA, which can like increase the carbon density. Here also, due to the previous SEM, we can see the silver and zinc nanosheets like these two like combined together, and it will create a lot of charge transfer channels, which will reflect on the EIS, the figure C. With the addition of silver, the charge transfer resistance highly reduced. Also, we got the best FE for CO and partial carbon density for CO, and also the best CO production rate. Here, in the right picture, I show you guys like the GDE mode and non-GDE mode. The GDE mode is like we sealed the inner part of hollow fiber. We let the gas penetrate through the hollow fiber. The non-GDE mode, we directly put the gas. We also sealed the hollow fiber, but we directly put the gas into the electrolytes. So it's a huge difference here. We found the carbon density of GDE in GDE mode like 5 times high than the non-GDE mode. Also, the charge resistance of this in GDE mode highly reduced. It's like we can see this hollow fiber configuration is very excellent to provide CO2 to the active side and accelerate the reaction. So in the third study, this work is mainly carried by my my colleague Yizhu. So we shape our focus on to like regulate the interfacial interface, the electrode and the electrolytes. So here we want to suppress the side reaction hydrogen evolution and improve the carbon density. So we also use the CTAB to adjust the interfacial interface. So here we see when the electrolytes continue with CTAB, it's actually in a disordered state. But when you apply the potential, the electrode becomes negative. There will be some charge here. So when you increase the potential, the CTAB ahead with the nitrogen positive charge will close attached to the electrode surface, and the tail of CTAB like it will be like in vertical shape. So it will form a very compact layer on the electrode. Due to this kind of interaction, so we see actually it can expel the water. Expel the water thus to increase the local CO2 to water ratio and facilitate the reaction of CO2. Also, this CTAB introduction also can reduce the charge transfer resistance from the EIS. We can say with or without CTAB. Without CTAB, they got a large transfer resistance. But if we got CTAB here, it increase the charge transfer and reduce the charge transfer resistance. Also from the figure C, a Tapir slope. The Tapir slope here is like with CTAB induction, we got a smaller value. It means the smaller value means faster electron transfer. So also we got good result for Faraday efficiency for CO. We increased the Faraday efficiency and suppress HER here. So in the fourth study, the final state study of here, we want to like to use the hollow fiber GDE to improve the pore utilization and boost the triple phase boundary and try to improve the carbon density to industry level like above 200 milliampere per centimeter, or try to reach the ampere level and use the high concentration of electrolytes. a previous study, we used low concentration electrolytes like 0.5 more potassium chloride and potassium bicarbonate. So, but so there will be some problem here if we use the high concentration of electrolyte because of the fast electron transfer in high conductivity of the electrolytes. Also, here is some situation here is also in here because our hollow fiber electrodes possess very high porosity. When you put it in the electrolyte, if you don't put gas in, the hollow fiber, the whole hollow fiber will be wetted. So here there will be some flooded pores and which the electrolytes fully wetted the pores. We don't have some gas penetrate in. So it's like kind of situation. If it's a battle between gas pressure and capillary pressure. So the capillary pressure, according to a Young equation, a capillary pressure is closely related to the diameters of pore and the wettability and the contact angle of pore structure. So one solution here, we try to uniform the pore size of the whole hollow fiber, or we can just reduce the wettability of hollow fiber. So in here, we choose the second way because it's difficult to adjust the hollow fiber pores to be very uniform because it's a very complex process. Here we introduce the PTFE. PTFE here try to increase the hydrophobicity of hollow fiber. So you mean not familiar with the PTFE, but you mean familiar with the PTFE tip? It's like when you try to fix some leaking problem the hose, water leaking, you can use some PTFE tips to wipe it out. So here is a similar function because we increase the hydrophobicity of the hollow fiber. So we can see the diagram here. So it's got three situations of the pore with the electrolytes. The flooded pores with like the pore structure is fully wetted by electrolytes. The partially wetted because is like around the PTFE. This part is like it's dried. It's gas wetted. It's dried so this will it will form some triple phase boundary here. It's like the water and gas and the catalyst. So this kind of catalyst size is like favorable for the reaction. But when you apply more PTFE, it will form a PTFE film here. So it's fully dried. So no liquid here. So but you lose the ionic and protons from the electrolytes. Also, the CO2 reduction also requires protons. So you don't you will have less activity for CO2 reaction. So from the we also observe the internal lumen side of the gas pressure here. When we applied PTFE, we found the pressure provided by the gas reduced. So it means the usage of pores improved. We also can see from the gas bubbling situation. So without applying PTFE, we saw like this bubble is like here, like this kind of situation. And when we applied the PTFE, we saw the whole electrode surface fully bubbled with different bubble shape. So we also conduct the confocal laser microscopy to track the fluorescent area of this configuration. So the figure E here is like we didn't apply any gas penetrated through the hollow fiber, so the hollow fiber is fully wetted. We saw this actually 100% of fluorescent area here. And when we apply the gas, the figure F is when we applied a certain gas penetrated hollow fiber, the fluorescent residue, this area, like water flooding area, will reduce. When we the figure C is like we applied the PTFE on the hollow fiber. This area further reduced, like compared to the first one, is like it reduced to almost 67%. All this evidence shows like we applied PTFE here, we improve the pore utilization for CO2 distribution. So also one good thing for PTFE modification is like we improve the stability of this electrode. So the left one have like 25 hours stability. The right one without PTFE modification only have like 7 or 8 hours stability. So the important thing here is like after reaction, the electron state of zinc experienced shift significance from the metallic zinc to oxidized zinc. When the electron state transformed, it's like the oxidized zinc, like some zinc hydroxide, will dissolve into electrolytes. So the catalyst will lose its activity and stability here. So all this just proved that when we decoration PTFE in the hollow fiber, we can improve the pore utilization and also increase the stability of the catalyst, also the electrode. So I got some conclusion here. So I mainly talk about the four studies. There is like we designed a zinc catalyst with different tailored zinc crystal phase by varying the CTB concentration for syngas production. Also, we try to introduce silver to zinc catalyst and create bimetallic silver sub-nanosheet to zinc nanosheet structure for silver production. Also we engineer the interface of electrolytes. Try to introduce CTB to suppress HER and improve the selectivity and current density of the hollow fiber TDE. Also, the final study we try to improve the CO2 distribution of hollow fiber TDE and try to create more triple phase boundary and improve the CO2R performance. The perspective here, I conclude in four parts. Like the fabrication stage is like we can choose different metals like copper, silver, bismuth, nickel, titanium for different reaction. I mean, if you choose copper, you can, because copper is like it's got multiple size. It can produce CO or formic acid or C2 plus products like ethanol and other useful chemicals. But for silver, it's mainly suitable for CO production, and bismuth is preferred for formic acid production. Nickel and titanium just more suited for hydrogen. But this kind of hollow fiber all be can use as a substrate. They deposit different catalysts. So also we can control the preparing process to control the parameters, pore size distribution, and the thickness of hollow fiber and the diameters of hollow fiber. It all can affect the final performance of this hollow fiber TDE. Also, we can nano-engineering this hollow fiber. First, if the hollow fiber itself can be catalyst side, we can use some like electro oxidation and reduction to increase its active size. Also, we can just directly deposit different nanocatalysts on the hollow fiber GDE to tune its selectivity. Also, we can dope in different elements like boric to tune the electronic stick and adjust the selectivity of this catalyst. Also, we can alloy in it like we make a copper tin, copper silver, copper different copper bismuth, different alloying for different product selectivity. The final is like to optimizing the electrolytes, like the case read the third study. I introduced the CTAB to adjust the interface of electrolytes and electrode. Also, we can use alkaline electrolytes, acid electrolytes to improve the electron transfer. Also, with different cations like chloride, different anions. So all these can affect the final performance of this electrode. So there will be a lot of interesting things can be done for this research. So finally, I would like to thank the support from Professor Hao Wang and Associate Professor Lake and from my group members and lab technicians, and support from CFM, also a collaborator from UQ. Also thanks the fund from ARC and DP project. Thank you very much.